In this video, we're going to talk about hypothesis tests for linear regression models. So we'll now expand on what we learned about regression lines earlier in the course. So I'm going to refresh your memory. When we calculate a least squares regression line in our calculator, this here, oh, let me get my pencil out. Is my predicted value. That's the y with the little hat on it. This b1 is my predicted slope, and b0 is my predicted y-intercept. We're trying to predict a slope and a y-intercept for our population parameters. Remember, if it comes from a sample, it's a statistic. If it comes from the population, it's the true value, and we call it a parameter. And that is with a beta, capital, it looks like a capital B, B1 and B0. So the population true least squares regression line, which we won't have because it's impossible almost always to get the population value, but if we had the population value, we'd write it like this: y equals capital B1x plus capital 1 B0, or beta B1x and beta B0. So what we're actually calculating, though, when we run a regression is the estimated or predicted, our predicted slope, our predicted y-intercept, and our predicted y value. All right, so for our first example, we're going to run through a regression example. So a doctor's interested in examining the relationship between a patient's age and total cholesterol. He randomly tests 14 of his female patients and obtains the data in the table below. The data are based on results from the National Center for Health Statistics. And if you look, we have age and we have cholesterol. We're calling age our independent variable and our cholesterol our dependent variable. And if we drew a scatter plot or scatter diagram, it would look something like our scatter diagram here. And we can see that there's quite a wide band of data around that line, our least squares regression line. Our least squares regression equation, if we is going to be, we'd run it in our calculator. We're going to put our first list, we're going to put our x data, and in our second list we're going to put our y data, and then we're going to go into stat, calculate, and then we want linear regression. Y equals ax plus b. And when we do that, we get our predicted y equals about 1.3991 x plus 151.3537. So our predicted slope is about 1.4, and our y-intercept is about 151. So our r value, if you have turned that on, is 0.718. And if we go and we check to see if that is a significant correlation, we can go to the table too. Our n is 14, and the critical value, if we look that up in the table, is 0.532. So we would compare 0.532 with the absolute value of our r value. And it is bigger, so there is a linear correlation. Our r squared value is 0.516. We get that by squaring r. Okay, so when we calculate a linear regression model, there's a couple of steps we do. The first thing we would do is we would have some kind of question of interest that we wanted to ask. You know, like, does my waistline have anything, the size of my waistline have anything to do with the percentage of fat on my body? You know, something like that. So question of interest. And then we would go out and get a sample and collect data. A random sample. And then we'd make a scatter plot. And we'd ask ourselves, is the data straight enough? Is it straight enough? Does it have any curves? Does it have a clear curve? So is it going to be linear? And we would have to look for independence. We'd have to ask ourselves, is our data independent? We should look at the residuals. Remember, that is the distance from the data to our line of best fit. Are they randomly scattered? We want them to be. And we could do a random probability plot. A normal probability plot on our residuals. And we would do that to see if they look normal. And then if they do, we would run a linear regression. But when we run a linear regression, we're estimating the slope and the y-intercept of the population. And we don't care so much about the y-intercept. What we really care about is the slope. And every data point, you know, when we were calculating a mean or a proportion, when we were doing hypothesis tests, our sample had a normal distribution. Well, this has a line of normal distributions. Each point has data point has a bunch of values that should be normally distributed about that line. So we need to take care and test to make sure that those are normally distributed. And if we do that, and we can say that it's within reason, we can interpret it once we've done that. So that's what we're going to focus on now, is doing a hypothesis test on the slope. So our null hypothesis is that our slope B1 is the population slope. We're saying that it's equal to 0. If there is no slope, then there is no linear correlation. And our alternate hypothesis is that our slope is not equal to 0, or we could also do less than 0 or greater than 0. If that is true, then that means that we have a linear relationship. If it's greater than 0, it means we have a positive slope. If it's less than 0, it means that we have a negative slope. So the test that tests this is a linear regression t-test, and you'll have that in your calculator. Our test statistic is a t-value. We're not going to calculate that by hand. Unless you want to, you could. But each problem would take you a while. Since we have to look up the t-value in our inverse t, and we need the degrees of freedom, the degrees of freedom are going to be our sample size minus 2, and that's because we have estimated 2 of our parameters, b0 and b1, our slope and our y-intercept. When we go to run the linear regression t-test, in our TI-83 or 84, you're going to put your X data in list 1 and your Y data in list 2, just like we did for the regression. And you're going to scroll down in the test till you find linear regression t-test, and then set the direction of your alternate hypothesis, and then you're going to hit enter, and it'll give you some of the values you're going to need. I'm going to use a mini tab printout for this video, but your calculator will give you the same, or the important information you're going to need. So from our first example, the doctor interested in looking at age and cholesterol, we came up with our total cholesterol, which is right here, is equal to 151 plus 1.4 times your age. We're going to use an alpha of 0.05, and the question is, can we prove a significant linear relationship between age and cholesterol level? So alpha is 0.05, and we're going to need to set up a hypothesis test first. So our null hypothesis is that B1 equals 0, and let's set our alternate hypothesis to B1 does not equal 0. That means that we have a two-tailed test, and that we're going to need alpha over 2, which will be 0.025. And then we're going to need T alpha over 2. And I do that by going to inverse T, putting in 12 degrees of freedom and 0.025 into my area. And T alpha over 2 is plus or minus 2.18. So that's the critical value I'm going to be comparing with. Okay, now on this printout, if I look at the slope, that's times the age, my t-value is 3.57. 3.57 is to the right of 2.8. So 2.18, this is my T alpha over 2. T alpha over 2 is less than my critical value. 2.18 is less than 3.57. And in and of that self, we would reject our null hypothesis. And just to double check, let's look at our p-value. We would be comparing that to alpha again. P over here is 0.004. That is indeed less than 0.025. So P is less than alpha, would also leads us to reject HO, or our null hypothesis. So we would say that there is a significant linear relationship, because if there wasn't, our slope would be 0. So having done that, we can predict the level of cholesterol in a 45-year-old patient. So we would just, in our equation, 1.4 times 45 plus 151 gives me a predicted cholesterol level of 214. All right, second example. A pediatrician wants to determine if a relationship exists between a child's height and head circumference. She randomly selects 11 children and measures their height and head circumference. So using the Minitab printout below, we're also going to use an alpha of 0.01. Let's go ahead and set up our null hypothesis. We're going to say that the slope equals 0, and my alternate hypothesis will just go ahead and say that it's not equal to 0. And that's a two-tailed test, so we have quite a small level of significance there. Half of that is 0.005, and that's on both ends. So we're going to need the t-value that goes with that. Our degrees of freedom this time are going to be 11 minus 2, so 9 degrees of freedom. And using inverse t and 9 degrees of freedom in an area of 0.005, I get t alpha over 2 equals negative 3.25 and positive 3.25. And then I go over here and I look at the t-value in my table, and my t-value, my critical value, is 6.63. So when I compare, t alpha over 2 is less than my critical value. 3.25 is less than 6.63, which leads me to reject my null hypothesis. That means that since the slope is not 0, there is a significant linear relationship between height and head circumference. And just as a double check back up, p equals 0, that's definitely less than 0.005. So if we were to predict the head circumference of a child with a height of 29 inches, we would plug that into our equation. And that gives me a predicted head circumference of 17.83 inches. My last example is there a linear relationship between the number of calories per serving and the number of grams of sugar per serving for a random sample of protein energy bars. A sample of 14 energy bars was selected, and the results are shown below. At the significance level of alpha equals 0.01, is there a significant linear relationship? So our null hypothesis, again, is that our slope equals 0, and that would be no linear relationship. And then our alternate hypothesis is that the slope does not equal 0, and that would indicate a significant linear relationship. And we're again using that small alpha over 2, but this time our degrees of freedom are going to be 14 minus 2, which will be 12 degrees of freedom. And when I look that up on my calculator, I get negative 3.05 and positive 3.05. And I can look up on my output here. T is negative 0.27. Negative 0.27 is going to fall in here somewhere. So T alpha over 2 is less than negative 0.27, or my test statistic, and this T alpha over 2 is greater than. So we would fail to reject that. And if I look at my p-value, it is greater than, it's a lot greater than alpha. 0.795 is certainly bigger than 0.005. So we would fail to reject. This t value, my critical value is not in the critical area. So we cannot predict the number of grams of sugar in a protein bar with 250 calories because we don't have a reliable way to do that. All right, that's it for today.